Atsushi Suzuki present provide for fixed domain. Sorry, I switched English. Yes, so this topic is somewhat related to simulation complicated three-dimensional kind of shape of simulation. But I have to back to something much more fundamental treatment of the boundaries by using these fixed domain method. It's based on old method. But I have to something to modernize this method, which works on the works well on the somewhat linear solvers. So issue is we can make sometimes good finite element method, but not so easy to solve by the linear solvers. So my concern is which is best way to combine two steps. So my presentation contains two steps. One is how to discretize, and the other is how to fit the discretized algorithm to the linear solvers. So as I said,
I said theoretically. No, no,
Je ne sais pas si c'est normal, mais le micro est coupé.
So you heard me? I think so. I will try.
Merci.
C'est bon. Okay, sorry.
Just beginning, so I would like to solve this kind of the problem with Lagrange multiplier. So by this setting, I can back to if I solve this problem with constraint, I can recover the different awesome problem inside large omega. This problem is concerned with full domain. So what I'd like to verify, kind of the Poisson equation is valid on original something flow domain omega in some form. This is easy to just I play with kind of Gauss-Green formula by setting of the test function on 0 on the deep boundary. In that case, I can recover a strong form in large omega. This is valid in omega. And then the same way, I can take of the function that is including of the data. This function is including of the data on the boundary. I can also recover the deep data. So because this is theoretic here, mu belongs to H manifold, and then we can get use the satisfied derivative. So here is okay, and then the same way, I can understand what is lambda. So also if I apply the integration by parts, this formula.
It's okay, okay, continue. I try to remove this. Masqué.
So try here. The lambda is equal to the jump of the Neumann data, the solution. The gradual tilde is correspond to Neumann data, and dot n is showing the value of the component, and then bracket shows that something difference on the either side. So this method is now is I only talking about continuous case. And then the issue is we have to think about this solution could be this system is solvable or not. So to ensure the solvability, we know the recursivity of the standard Poisson application. Even though it is depending on the concerning domain. The most important issue this is kind of the constraint problem. We have to think about if so-called if function is satisfied or not. But in this case, just this integration is purely here. So it's very easy to verify. This is each function is established very natural thing. Just famous definition with h minus half node. So in the continuous case, it's nothing, no difficulties. So we can see if we like to put the triple data in something quick sense, Lagrange multiplier works very far. But the issue is after this integration, so-called if condition is not so straightforward. In this case, is this is analyzed and published on the 1995. We have to use something of the large mesh for Neumann data with somewhat low approximation P0 element, but the size should be almost 3 times large compared to the primary data. So this is somewhat something strong description if we try to apply in engineering problem. So this boundary I have to carefully track of the boundaries and then to locate of the approximation point on Neumann data carefully. So anyway this method is something attractive. And the other way to think about Lagrange multiplier is just put the data on pointwise on the boundary. If we know the boundary exactly, and where is the degree point is known, we can put that is in pointwise by using Lagrange multiplier. So this one is just B is showing Boolean matrix. Where is the degree point? And in this case, is the mixed function is very simply understood as kind of the randomness of the mu. That means we transpose to multiplied by Lagrange multiplier data. But if that is the result is 0, mu only satisfies 0. That can ensure the solvability of this linear system and the KKT system. So this is kind of extreme case. This all mesh point is fitted on the boundary, and data is given back. So here is somewhat with if functions is easy. So we don't much worry about that. Then is my plan is how to solve this kind of the non-matched mesh to the boundary. Here I have something removed from the circle from the square region, and then closely look. This boundary is not smooth. Then this is somewhat internally one layer inside. There is actual boundary. This is circle. So in this case, is the mesh subdivision is no need to fit the boundary. So we don't need to use body fit. So this makes something relaxed the usage of the mesh generator. In many cases, if we proceed with the shape optimization, boundary is not become smooth, normal smooth, and then we are very hard to make some appropriate mesh. But here, just the mesh needs to be something gathered close to the boundary. And also this allows the kind of the non-smooth boundary. Just the boundary could be expressed by the regulated function. So then I'd like to think about how do we implement this method on this configuration. So what is the zero level set is expressed by function p. And this one is also not continuous because of the P1 approximation. So that means the P1 P is level set of zero level set consists of the segment, sum of segment of the point. And then now is I'd like to put the Neumann Lagrange multiplier for Neumann data. In this case, I will pick up the triangular touch to the boundary. It's not something of the vicinity of the boundaries. This is one layer I'd like to define. This means element is at the intersection to the approximated boundary. And then is this integration, surface integration, can be expressed by segment wise. But the place is defined by the level set. And then so fortunately, PFM already have this functionality. It needs to be right the level set because there's something function. So I can easily express by PFM. And then there's the idea to approximate the vehicle data on the target point. So this polygon. The rule point, this can be represented by red points, and then interpolation. We can take some interpolation of the, but this is actually automatically done inside the data. So, but in the important issue is vehicle data is approximated by P1. Neumann data will be approximated by P0. Just I can show, I can write the function space. And then the last thing is the matrix is obtained as this KKT system, ADB transport B0, very close to the Stokes equation. So if the linear solver is clever enough, this could be solved. And then is I talked about kind of the implicit functions. That is proven in the 20th it use the kind of restriction on the approximation of the Neumann data. But by this setting, I think this matrix seems to be invertible. So there is no problem on the by linear solver. But I said the linear solver is clever enough, but unfortunately, one pass fails. So that's the error happens, the short of memory. So we have to do something modify the Mapas code or modify of this setting. That is my today's topic. So issue is something the net vicinity of the element data. This is inside of the domain. I have the sample, and this element is covered with sample. So if you closely look at the inside, there is actual boundary line here, and the range and yellow is covered with the. This is a set of the edge touching on the interface. So the idea is to stabilize this method using adding some term of the diagonal of the D. There's a very similar idea to stabilizing the Stokes equation. It's kind of the similar, same to kind of the how to say kind of gradual form. It's ideal to use. But this is already done in around 13 years ago. I picked up this paper in the fixed domain method using that element. This is part one, using stabilized fragment multiplier. Part two, use a Nietzsche trick. And that is not concerned about this KKT system, but control number seems to be strongly dependent on the mesh. But here, thanks to the Lagrange multiplier, matrix becoming indefinite, but control number is something moderate. So I'd like to take this. The issue is how to stabilize the Lagrange multiplier. This is the issue. So then the paper explained is we have to take all the cases and start crossing of the level set above the original boundary, and then to compute the something gap on the above side and the downside of the surface F. This is the definition of the bracket is difference of the plus or minus. Sorry, this is not plus one. It's plus or minus. And HF is diameter of this segment. And F is something phase is inside of the this we can see the several segment that is crossing over the interface. So then this is calculated, like if I use the P1, P0, lambda is only take one value, each inside of each element that can easily computed by using of the each element. And this integration is just here is value is constant, right? HF becomes HF square, and then this is something very easy way to calculate. So here by this way I can add something of the positive supplement to the value term. And then there is a kind of the stability parameter, same as the standard stabilization technique. And then one trick, is important trick, is this has HF right here. And then this paper shows kind of the proof of the convergence using the mesh dependent node, using of this HF. So then it seems to be okay. And then also the good news, this system is much more stable than previous one. So then is I'd like to emphasize how this works well for linear solver. Next slide. So usually we will have to think about KKT system that should be solved that satisfies two issues. One is coercivity for block A. The next one is the function. This is famous for sophistication or another sophistication. Then, but issue is if I proceed factorization in some sense of the by pivoting, but the factorization is based on kind of the local generation of the short complement. And then if the short complement S is become 0, linear solver fails. So because of this is 0, it's not so clear we can proceed the factorization in direct way. Then we have to be careful. So we need to choose better factorization solver. But this is kind of possibility, even if we know the whole system can be factorized, but during the computation it may fail. And then, but if we have this is minus C, of course, maybe we can assume P is we transfer the current is possible. But if I change the sign of the second line, the full system becomes coercive, which means any kind of linear solver can be this. So thanks to this solution term is we can relax of the something demand for linear solver. So the issue is I found the way to manage to add some term for stabilization. That is unfortunately this term does not satisfy Galenkin orthogonality function, but the weight is controlled by HF square. So the error is not not affect to the for the solution. But if we have to really work with kind of we can combine so-called the symmetric mode and then and the mappers also can do everything done. But to do this one is something of the selection of the pivoting. Mappers will sometimes exhaust working memory, so we have to be careful. So then is I will show what I can write by real-time implementation. So fortunately, by using trunk function, I can extract the unbounded domain, and everything can be written as kind of the in sense of the continuous or something. I think this is somewhat acceptable way by creating. Even I have to define block models. Then this one is the key point is here. Regular reset is defined by implicit rate. If it's kind of the function. So this means internal is negative, the outside is positive. So then I do some other mesh to show the F. And then is this is trick to use trunk. I do something of digitalized to 1 or -1, and then I can something choose the criteria here. I can extract the content. And then I can define by a form or by using standard Boson form, and then plus integration of the level set integration, the THD. THD is something bounded domain, and the level set is F1. F1 is a function of this small region, expressed like 1, and if you times this is finding duality here. H half and H minus half. This is written by Hilton in the products. So but by this way, I can divide of the matrix, and then I can send it to numbers. I could get a solution. But by stabilization term, it is slightly not so easy. Just I have to play this kind of element wise. So maybe I have to write much more cleaner way. But I selected all the segments one by one using those adjacent function, which is can find the element which is locates on the either side of the edge. And then this is between the edge, I have to pick up all the edges, and then I have to take manage of the degree of freedom by something 3 stage. And then finally, I can make some sublet matrix. Then is I could get solution. Then this is something like that. Left side is use kind of the approximation close to the boundary. And then this internal boundary is not completely smooth. It's one layer extended. And then the degree of freedom is around 3000. And then for the degree of freedom, the Neumann data is around 900. And then the right side is standard mesh. And then almost same degree freedom. So if I put the delta is 0.1 stability parameter, and difference between two solutions are around 0.1 in relative error. So I think this works fine. So maybe I have to extend this for the specification, but I'm something interested. We can use P1 approximation for Neumann data. Here is a P0. Of course, I can change something slightly the Fictitious code. But if I use P1 data and without stabilization, it's also I can get a solution. But error is twice worse. Maybe stabilization is somewhat very essential to do that. And then to proceed that one, I have to something modify the number scope plugin to relax of the working rate to 200%. And this is partial. So, but I'm not yet successful to find the stabilization method to Lagrange multiplier. That is approximate P1. Because this is not so standard way. But the Lagrange multiplier is H minus half. P1 is not so good ideas. So that is my presentation. So thank you. Advertising for my activity in Japan is I sometimes how to switch the so I do something of the some school on the advertising curriculum in Japan. So this is the schedule on the March 15. This is by through internet. And then this timetable is unfortunately starts from Japanese time, but afternoon is their countdown session. And unfortunately, we can provide you kind of test account of Fugaku. So if you are interested to participate, please access to this website. We can that is school. So deadline is right, that will be next month. So I'm looking forward to you.
This is in English or in Japanese?
English. I thought but English, but not French.
No, I'm sure not French.
This is my thank you.
So thank you. We have time for question.
I would have expected that you would not take such a fine mesh near the immersed boundary.
Maybe that is something.
So the question is, does it work when the mesh is coarse near the boundary? No. Why not?
There is maybe something of the constant is big of the of course we can get some kind of first order convergence of the even that is without the Lagrange multiplier.
Because the mathematics they use square root of h.
No, it's just that is if boundary is approximated by polygon.
Yeah.
Starting with polygon, this is the order is h. So yeah, but maybe I think is to use the refinement is constant is much better. That is to Yeah, maybe, but not a good idea to use completely regular background mesh. So that is something I combine with mesh refinement, but not free refinement. So this is kind of taking mixture of two things.